The fate of the universe. Friedmann equations. The evolution of the universe has always been a mysterious problem. Hundreds of theories have tried to describe such an existential topic, both from a philosophic and a scientific point of view. How and when was the universe formed? Is it infinitely big? Will our universe die? These are just some of the questions that we would like to deal with when talking about universe. Most of us will say that it's almost impossible to answer even to just one of them, but they might be wrong. Did you know that there are 3 equations, called the Friedmann equations, that can help us find a solution for all these incomprehensible interrogatories? Do you want to know more about them? Stick with me and I'll tell you everything in a moment. Several different views about the universe started to arise during the 19th century with the development of astronomy and the use of telescopes. The major belief was that our universe must be stationary and infinite, like a little balloon that never changes its size. Unfortunately, nobody managed to create a theory that explained how the universe was formed. As a result of that, the scientific community was considering our world as something that has always existed, something totally immutable, boundless, and infinite. Therefore, this structure was proved to be wrong by a simple paradox known as the Olbers paradox. Have you ever heard anything about that? It just tries to explain why the night sky is dark. Even if it seems to be irrelevant and useless to describe something we see every night, this little paradox has taken us to astonishing conclusions. As a matter of fact, the night sky can be dark only if the universe is limited in space or time. Let's try to understand why. If the universe is infinitely big, we can find a star in every direction of the sky. And if it's infinitely old, enough time has passed for the light of that star to reach us. Consequently, the night sky should be really shiny and bright in every direction. Since we see a dark sky, we have just 2 options left. The first is that the universe is not infinitely big. There are no stars in some directions and those areas will never shine. The second is that the universe is infinitely big, but not infinitely old, so that the light from some parts of the sky is so far away from us that it would need more time than the age of the universe to reach us. This little paradox has a great power and is considered to be the foundation of modern cosmology, the science that studies the development of the universe as a system. Since the universe is not infinite, this suggests that it has to change during time and that it has to be formed in a detailed way. As a matter of fact, with the beginning of the 20th century, scientists were very puzzled about a possible description of the universe as a single system, and they created a theory that would definitely change the way we perceive our world. The theory of Big Bang. Firstly, 3 physicists called Robertson, Friedmann, and Walker developed a strange way to locate things in space. Usually on Earth, everything is described by 2 coordinates called longitude and latitude. The same can be done with space, but the possibility of an unstable universe that might expand or contract required a different type of coordinates. The 3 scientists came up with a great idea that was really useful to describe such a phenomenon. They introduced the so-called scale factor R that describes if the universe has expanded or not. A good comparison can be made with an air balloon similar to our Earth. Let's imagine that it has a scale factor, R equals 1, and a little point with its coordinates is drawn on it. If we inflate the balloon and its size doubles, the point will always have the same coordinates, but the balloon will be bigger than before and its scale factor will be R equals 2. In physics, we say that the point is located by a system of co-moving coordinates that don't change in time, and the size of the balloon is described by the scale factor that changes in time if the size increases or decreases. This system is also known as FRW metric. Furthermore, this useful type of coordinates depends even on a curvature parameter called k that describes the shape of space. There are 3 types of curvature: flat, k equals 0, like an even ground; positive or closed, k equals 1, like that of a spheric object as the Earth; and negative or open, k equals -1, like that of a Pringles potato chip. What is the curvature of our universe? Our universe is supposed to be flat, but we'll discuss that later on in this video. In 1915, Albert Einstein published the general theory of relativity, one of the most successful theories in the history of physics that resulted to be a crucial element in the development of cosmology. As a matter of fact, 7 years later, Alexander Alexandrovich Friedmann developed the three most famous equations about the evolution of our universe by using Einstein's discoveries in the FRW metric he helped to create years before. The Friedmann equations are partially deliverable from Newton's gravitational theory of the 17th century, but the math might be a little tricky and puzzling, so let's just try to make it simple. What are those equations about? They are three laws that link the scale factor of our universe to the space curvature and some other parameters that can be measured observing stars and galaxies. The first one shows that the velocity, which is the change of the scale factor, is linked to the density and the curvature of our universe. The second Friedmann equation deals with the acceleration of the universe. That results to be always negative. Consequently, the rate of expansion or contraction is slowing down with time. Finally, the third law, also known as the fluid equations, describes the correlation among the change of the density, the pressure of radiation, and the scale factor R. The first one favors a contraction because matter has a strong gravitational force that tends to gather everything together as the sun does with our planets. On the other hand, the pressure of radiation enables a possible expansion. What is pressure of radiation? The universe is filled with electromagnetic radiation, like light, X-rays, gamma rays, infrared, and other types, that has the ability to warm objects. We experiment this when we take sun rays at the beach, for example, but even to have a small pressure on things similar to that of a wind. As a result of that, the presence of radiation goes against gravity and might slow down the contraction or cause an expansion of the universe. As a matter of fact, we distinguish between a radiation-dominated era and a matter-dominated. This law predicts that the density is bigger if the scale factor becomes smaller. This equation is the main source from which the idea of Big Bang came up. At the beginning, the universe was extremely dense and small, and after a period of expansion, it has reached the actual size. Moreover, these equations are a powerful tool to derive the age of universe, which happens to be around 13 to 14 billions of years. However, the most important parameter that can define the real evolution of the universe is the curvature that appears in the first equation. If we live in a flat space, k equals 0, the scale velocity is positive. The universe will tend to expand at a decelerated rate, stopping in an infinite time. In this case, the density is called critical density. Instead, if we live in an open space, k equals -1, the density will be smaller, the velocity bigger, and the universe will expand at a constant rate forever. The galaxies will be so far away from us that their light won't be able to reach us. The night sky will start to become darker and darker. Moreover, the space will become colder and colder. We call these possible end of the universe Big Rip. On the other hand, if space is closed, k equals 1, the density will be bigger than the critical one. The velocity will decrease, becoming negative. The universe will start to contract, returning to the size it had in the first instance of its life, the Big Crunch. Could you imagine that the fate of our universe depends on small changes of a parameter? But what is the actual curvature of the space? How has it been measured? We previously said that space is almost flat. This result has been calculated by measuring some elements of the cosmic microwave background, a radiation that fills space and is like a last emission of the Big Bang explosion. This light is almost uniform in every direction, and the size of the small differences in intensity indicates that the curvature parameter is nearly 0. Consequently, at the end of the last century, physicists thought to be in a flat universe expanding at a decelerating rate. However, they were proved to be wrong by an astonishing discovery. In 1998, a group of astronomers, led by Samuel Perlmutter, was measuring the light of several supernovae, explosions of big stars at the end of their lives, and they noticed that their light was fainter and more red than expected. In physics, this effect, called redshift, means that the universe is expanding, and the lower intensity measured means that the supernovae were further than expected. As a result of this discovery, scientists suggested that the universe was expanding with a positive acceleration. Instead of slowing down, it was speeding up. After that, Perlmutter and his group received the Nobel Prize in 2011. Are Friedmann equations wrong? What is the cause of acceleration? These are the two main questions physicists tried to answer in the last 20 years after Perlmutter's observations. It was crystal clear that Friedmann equations needed to be modified, and a small but significant alteration was made indeed. In the first two laws, a cosmological constant was added. This quantity is positive and is a sort of addictive pressure opposed to the gravitational contraction. It was first introduced by Einstein, that lately admitted to have probably committed an error and described it as his biggest blunder. However, the cosmological constant resulted to be perfect for the description of the accelerated expansion through the Friedmann equations. The addiction of this quantity made the acceleration positive in the second law, and it can be considered as an extra density. Unfortunately, it's totally unknown what the constant represents. What is the cause of the acceleration? Scientists think that the universe is filled with an obscure energy called dark energy, which opposes to gravity. The major problem is that through various measurements, physicists found out that dark energy is nearly 70% of the universe abundances. Its impact on the evolution of the universe is way more important than the density matter. Finally, the universe is almost flat and is expanding at an accelerated rate. If this trend will continue, the universe will end at a big rip, a cold epilogue with all the galaxies very distant from each other. However, we know very little about the dark energy, which is the most predominant constituent of space, and more observation are surely needed to find out more about the fate of the universe. This video ends here. Thanks for watching, everyone. Did you find this topic exciting? Are you amazed by the possible endings of the universe? Are you afraid by discovering that it could all end in a big crunch or big rip? Is there anything more you want to hear about time?